Hello everyone, this is lecture 26 of Petroleum Reservoir Geomechanics, PTRE 465531. We'll carry today with module 3, where we left last time. Before we do that, I did upload a new version of the homework. I didn't change anything important, of course, but in case we fixed some mistakes, issues that we found last time. Basically, here there was a double plural. It was saying earthquakes occurrences, but it should really say earthquake occurrences. If you don't need to use two plurals, just like the second word make it plural. I had an extra, basically repeat of, so if you use equation 1, the way I have it here, the way we learned in class, which we said is very important, it's going to be very important for exam 2. This equation implies that tau naught is equal to 0. So you have no cohesive strength. It's like the rock is assumed to be pre-fractured or non-intact. Look, I made another mistake. Non-intact. Basically, if I tell you it's intact, it means that there is a tau naught. That's like in the lab making an experiment like a Brazilian test or a UCS test or even a CS test on a core sample. When you hold the core sample, it holds together, okay? So you assume that it's intact. Now you can do a confined test on a non a pre-fracture sample. There are ways you can do it. I cannot really show you in class really how you can do it. It's a more hands-off thing. You need to have a vessel where you put your sample inside a nylon jacket, which basically holds it together because it's pre-fractured. And then you put water around it with a pump. And this is how you apply the confinement. So you can do a confinement strength test on a pre-fracture sample, but a UCS test, a Brazilian test, it requires that the sample is intact. That means not pre-fractured. And tau not equal to 0 automatically. So I did clarify that. I guess I will fix the end that is missing. It should be non-intact rocks. And then there were some instances here where I think the system did not update properly, say equation 3 here, and equation 3 somewhere later. There were two references of equation 3. Okay, one is here, and the other one is no idea, but here. Okay, so those are fixed. And I added one line. You will need Simpson's 1997 equation for alpha phi we learned in module 1. Excuse me. Now it's not just module 1 that I showed you this equation, it's also in module 3. So if you want to do section 3 of the homework correctly, you need to use that equation, obviously. And it's available in the lecture slides, module 1 and module 3. And of course, online you can find it. Lunster has an alpha phi AA phi calculator in his website. It's not easy to use that for this homework, but I mean, this is for the website, I guess is for everyone. Everything else stayed the same. I want you to submit a spreadsheet and a PDF. The spreadsheet will have 5 tabs. one has a stress polygon without poroelasticity, the other one has a Mohr circle without poroelasticity. Then the third tab has a stress polygon with poroelasticity, and then the fourth tab has a Mohr circle with poroelasticity. And then you have another tab with the two alpha phi versus stress plots. It's better to have them together in the same tab. Now, if you want to make it a sixth tab, I'm still okay with it. Just make sure that TA knows he's not going to take points if you make it 6 tabs instead of 5, as long as you have all the deliverables. And then the PDF summarizing everything with screenshots. Everything else should be okay about this homework. Now, I didn't have any visitors in the office hours yesterday. I almost fell asleep. One time I really did fall asleep. Yeah, I mean, if you guys have any questions, me and Kalu, the TA, are available by email, by office hour, in office hours. If you want to book an appointment, you can. Please do so. These are easy points, and obviously there is also the bonus for extra couple of points. Can you think of another scenario involving human activity in which in the subsurface that can potentially trigger such seismic events? There is a very good example. And then there are some other examples that are good. I'm willing to hear. I'm really expecting to hear that one example that I have in my head. And it's very possible to trigger induced seismicity. And then there are several other examples that really don't make sense. So you need to think about, okay, what is the process that we do with SWD? We do something. Is there any other process, any other activity, any other operation other than SWD that does pretty much the same thing? Maybe with not salt water. This is what you need to think about. And I think it will be easy to get it. All right, so let's see where we finished last time. I think there was a couple of slides that we finished this. Okay, and I believe it should be clear to you right now how to draw this. I did it a little bit fast 2 lectures ago, and then I did it slower in the last lecture. I think it should be fairly easy how to draw this plot. Okay, we'll proceed basically with the same subtopic. We're talking about shear failure, right? Shear compressive failure. And this is part of what this module is dedicated on. Now, in Cartesian coordinates, the normal stress is given by this equation. C is basically, I think we called it theta before. Some people call it V, but it's basically the angle that we are looking for in terms of, I have this, I apply as sigma 1 on top and the bottom along the axis, and then I have sigma 3 on the sides, on confinement, not just on the sides. Sigma 3. So I don't care about sigma 2. It could be the same as sigma 3, it could be bigger, it cannot be bigger than sigma 1. Okay? The combination between sigma 1 and sigma 3 using this equation dictates the normal stress along a pre-existing fault that is at an angle psi. So this angle C. We used to call it theta. Some people call it vita. Calling it theta in the more Coulomb diagrams, more circle diagrams, we did. It was a mistake of me because we are gonna be using theta for another angle later on. So I don't want to be causing confusions. It's like what I did with mu. I knew we are gonna use mu for a different parameter. So when we did the Lame's second parameter, even though he uses mu, I didn't want to use mu because then we have another thing for mu, and then you go to your reservoir classes and you have another definition of mu. Therefore, it's completely different. I don't want to get you confused, drowning Greek letters, symbols. But when I did the angle of the Mohr circle and I used theta, I should have used beta or C. Okay, and this is the stress. Let me draw it using orange. Okay, this is the pre-existing fault. This is the normal faulting. Sorry, the normal stress here on the fault. It's at right angles to the pre-existing fault, right? There you go. And this is what sigma 1 and sigma 3 are when sigma 1 is working against. It's trying to create shear along the fault tau that will exceed this sigma ni, the normal faulting, sometimes called sigma ni. And tau is given by this, okay? Tau is given by this. And these are the equations that you can put together and come up with. If you put them, remember we said for, oops, sorry, remove this. Now, if you do this, this is a pre-fractured rock, right? So tau equals mu sigma n. If you use these definitions for tau and sigma n, you are gonna end up to what we said before, equals to that expression square, mu plus 1 plus square root of mu square, the expression on the right hand side of the equation that makes it equal to 3.12 if mu is 0.6. Basically, shall I erase and go back? This expression here. That's how we can get it. I mean, it requires a little bit of derivations and then some manipulation with the angles. But yeah, that's how you can get it, basically. The 3D Mohr circle displays graphical representation of the stress tensor in all its projections. And actually, the Mohr circle, like I said before, is not just for shear failure. It can also do tensile failure. We don't do it in this class, but there is a lot of stuff you can do in the Mohr circle or the polygon as well. Anything you can do in the Mohr circle, you can do on the stress polygon, by the way. This is sigma n or sigma nn. It's a pre-fractured rock, so I start from the origin, I go up. Slope is mu. And then I have sigma 1 and sigma 3. Now, if I cut the line, I have failure. If I don't cut the line like now, I don't have failure. What about now? I think I'm gonna have failure now. Okay, now I have failure. in this region. Okay, so I go in the middle. I think it's in the middle. I take this angle, and I take this angle. This is 2C1. This is 2C2. The angles from C1 to C2, that's the fault angles that I'm going to have failure at. Right, that's the fault angles that are giving me failure. And I need to, basically, if I have pre-existing faults in those orientation, I'm going to have like slippage. This is what the Morse circle is indicating. There is more complicated examples, no, complicated applications of the Morse circle. Yeah, it gets it can get complicated. The thing is that you guys need to know about stereo plots and stuff to get that, but I don't think, I don't think the classes that you took before, I don't think they do that in the geology classes that they took before. So if we have more time at the end of this semester, I think we are good with our material so far. I may come back and show something. I remember when I was taking geomechanics, we did a lot of stuff with stereo nets, but was if we are going to have geologists in this class next year, I will have to put things with stereo plots, so it will be hard for the engineering side of the student body, I guess. But everything else, all the linear algebra stuff, it will be easier for the engineering side, harder for the geology side. Anyway, critically stressed pre-existing faults and permeability. A critically stressed pre-existing fault is basically a natural fraction which exhibits a ratio of tau over the normal stress of 0.6 to 0.8. We have already said that, it shouldn't be new. These pre-existing faults are said to be critically stressed because they are practically falling or just about to fail in shear. So it's very easy to make them fail. They are just about to reactivate, slip basically. Natural pre-existing faults can help fluid drainage. Traditionally, fracture permeability has been thought to be only proportional to the normal stress that holds the fracture together, because basically this is what restricts the fluid from flowing through that fault. The concept of critically stressed PEFs or the critically stressed faulting hypothesis, which is not new, but is not old at all, I think it's from the 80s, alters fracture permeability such that is now proportional to both tau and the sigma and the normal stress. So it's not just the normal faulting that is being affected, it's also the tau. Also, you need to take into account if the fault slips, it's going to impact the permeability, right? Implications on fractured reservoir.
Permeability of the fault or the reservoir?
The overall permeability of the reservoir, also the fault, right? Through the fault.
Why the reservoir, like because of compaction?
No, because fluid can flow through that fault. Yeah.
But what about the natural, like primary permeability? From the normal pore.
No, it's part of the reservoir, right? So
Yeah.
it will affect
Yes,
the total, the average.
the fluid flow. Yes.
Yeah, it will affect it. Now
It
it
doesn't affect the pores and fault roads itself.
No,
It's not like hysteresis or something.
no, because if you have, let's just say we have everything that you do assumes homogeneity, the pre-existing fault is part of a heterogeneity, like, so you don't expect it to be there, but you still feel its effects, right? It does impact the fluid flow, but so it will change the value that you're reading, but you cannot model, it's a discontinuity in your system, right? If the fluid goes there, you might find it going 1 mile away, right?
You change the direction, yeah.
Yeah, right. Or you may have sweep problems,
Yeah.
or certainly, I mean, if the fluid goes
And
there.
it can cause quick depletion as well.
Yes. Like my other advanced drilling professor used to say about the biggest fracture he encountered, or he thinks he encountered during his career, was 7 miles long. They were producing mud from their well, like 7 miles away.
Yeah, one time in Iran, when people were drilling gas reservoir. Was
Iran,
between Iran and Iraq.
Iran and Qatar. If it's gas, must be Iran and
Yeah,
Qatar.
they were drilling there, and at some point they hit the fracture zone and
Oh,
the village like very far away. And they imagine the whole village burned out
oh wow.
because of one guy lighted the cigarettes or something like that.
Also, they were producing methane,
Yeah, from the
and
other
they
side.
didn't know
They
it.
cause instability in the.
Oh, it happened here, Aliso Canyon in
But
2000.
one well, when you're drilling a well, cause the stability of the fault. And
No, that one was a storage well. It was a gas storage well, and it was leaking. And then I think it caught fire in California.
But how you're drilling a well can cause leak into the initial reservoir? Is that possible?
No, because you encountered the gas zone, and then gas somehow found its way up through your
Well, and it went through the.
So there is 8 ways I think you can leak through. We do them in well completions, like interface between the plug and the casing, if you have a plug, if it's a plug in abandoned well. You have the interface between the casing and the cement on the other side. You have the cement itself breaking, you have the casing itself breaking, you have the cement and the rock interface. Bunch of stuff. I think it's
Like-
6 or 8 ways. you
Like
can
the
do it.
blue out in Santa Barbara.
No, that was, they didn't even have casing on the whole well.
Yeah,
Almost.
that's
So,
they did just the casing at the beginning. They drilled
yeah,
like with an inclination, right?
yeah.
They went through like how many feet they drilled?
But also
through
it's a
the-
strike slip faulting there, so you already have a lot of faults. It's a very, very tectonically active region.
Yeah,
If you
but
think
why
about
you can put casing? I didn't get it.
it was a very easy well, and there was a law to get, you need to get casing up to a certain point, but they were getting waivers for those wells. Because that
Waivers?
was, yeah, you can get a waiver and basically don't follow the law, but you get a waiver for it. You file for a waiver. And remember, this was the 21st well that platform had drilled from that location. So they really knew what they were doing. And it wasn't a very big, it was a pocket that they were, a gas pocket or something. Oily, light oil
But
pocket.
yeah, like oil, so they waste a lot of money.
Oh yeah, it was like
It was a big reservoir.
80 million gallons.
Yeah,
gallons.
83.
Huh?
83.
83 million gallons.
Yeah,
That's a lot. Yeah, that's a lot. And it was a tourist area. I think it's nice. Well, that's why that's where we started, because it was this. And remember, it was this. It was February of. I think the blowout happened on 28th of January of 1969, and they couldn't stop it until February 6th. Because every time they were going to stop it, they were getting oil flowing from other places. And you can't do anything about it.
But they put a cap after that, right?
No, after that, I don't know how they capped it, I think the same way they were trying to cut it, but at that point the reservoir depleted, everything was produced. So
Everything was wasted, right?
everything was in the water, and then massive ecological disaster, and people were shouting, and that's when the earthquake started.
Environment people were like,
Yeah.
went to the street and they were very like,
And then because it was also the hippie era at the time,
or hippie.
And it's not that far away from, like, there is a
peace and love stuff.
no, it's like how do you call it? There was a place where hippies used to live, not far away. I know San Francisco, but not far away from there in Santa Barbara. So they had to. I think it was '83 when they finally said no more drilling new leases in California.
But they went to the court.
Yeah, they went to the court.
But I guess they won because they have the waivers and stuff. And even USGS got in the investigation, right? Yeah, but no, they didn't go to the court before. I mean, it was like you filed for a waiver from the regulatory agency. Yeah, but they had those waivers, so it's not their problem, basically. Well, I mean, they didn't know it would be like this, but yeah, I mean, Chevron or Union Oil. Union Oil also. Yeah, it became Chevron. Yeah. And if you talk to all people that used to work in that time, they will say the same thing. We didn't run enough time on that well, in that well. Like somebody, a foreign student, was telling me that in his place, you only need, when you cement, you need to get 100 feet of cement above the shoe, and then you are fine. Really? Yeah. You can. I mean, you are fine until you are not, I guess. But so it's like if this is the case in shoe, I only need to do this, and then I'm good. All this can be open hole. Really? All casing, but empty. Is it like low permeability reservoir? Must be. Or shale maybe? No, must be offshore. I think it's offshore. So it's very deep wells with many layers of casing. Oh. So if you break one, and also, I mean, if you make sure the casing doesn't chemically degrade, it's harder to break the casing than breaking the cement or the rock. So the casing should be the hardest thing to break, but also the casing can be chemically rusted and stuff. Imagine we had like a problem in Algeria, and now it becomes like a whole stuff going there. It's like because of salt. Oh, they didn't cement very well, and some water. Like a cave? Yeah, some water went go through between the casing and the cement, and it hit the salt formation. Well, in Texas now they have what they call. It's still increasing. Yeah, they have what they call now. That lady I was telling you last time, the one that got naked and climbed on the pump jack to run for the railroad commission. Mm-hmm. They call them zombie wells because basically you have a lot of wells and you plug them and you leave them there. And you plug them and they are okay because you don't assume the pressure will go up. But then you start injecting another place for water flooding, and water goes to that old well. The plug doesn't work very well, it flows in the air, and then you start leaking brine from the well. The brine is okay, brine is not terrible, but imagine if you leak something else. So it can be a bad thing because I mean, you plug it and abandon the well and then you leave, right? You don't forget about it. You don't expect. They plug it with what exactly? Well, they follow the rules. Every state has. I saw even some wells were plugged with a high density cement. Yeah, or you can put a bridge plug. Yeah, and bridge plug. Cement it. Depends. I think in Texas is 100 feet of 1 microdust, something like that. The cement, something like this. There is rules, yeah. Yeah, but the cement can break, right? Yeah. After some time, and it can degrade chemically with time. Yeah. PEFs have an orientation that favors high tau over sigma E ratio, are said to be critically oriented. That's the ones that are easier to sleep. If critically oriented PEFs exhibit higher permeability values,
than non-critically oriented PEFs, then the stress state determines which PEFs are hydraulically conductive. That means they can pass fluid through them. And also determines the permeability anisotropy in fractured reservoirs. This dependence is particularly important in unconventional shales, where fracture permeability plays a critical role in determining production flow rates. So when it comes to shale, there are several natural fractures, especially shale plays like the Marcellus in the northeast of the country. It's known to have calcine field intrusions. Basically, it's shale, but when you see, it's like in the oil field, we used to call it Oreo cookie. Like you get drill cuttings, you put them under the microscope. Well, we had that in the Permian, and it would be like black with a little bit of white in the middle. And it's like, oh, I got an Oreo. Basically, it means that it's a shale with calcine field intrusion. It's like a mineral within the shale. And they can play a big role. I had Dr. Lee from OSU, Oklahoma State University, Hanju Lee, did his whole PhD in looking at how does interaction of hydraulic fractures with these calcine intrusions will impact the way the fractures are propagating. Let me show you something from his paper since we have some time. Hanju Lee, Gabe, also Walter, 2015. Okay. Look at this. So what happened is that ExxonMobil gave him a core with calcine intrusion. You see that? And then he cut samples from that core with the calcine intrusion being at different angles. And then he did a laboratory test called the semicircular bend test, which is very similar to the UCS test. Is run in the same system, but is for something else. You measure a property that is called the fracture toughness, and that property basically says if you already have a fracture, how easy it is to propagate that fracture. So you have to cut a sample in a certain dimension and then put a notch here
and make sure that it's not gonna refract again.
Yeah. So he's gonna try to he tried to make them go through. So you have let's see, what are the pictures? Oh, okay, here. You see 4 different responses here. Let's see. Oh, it says that here. Diversion, fracture moved like this, and then hit the calcite.
The main fracture.
And then went along the calcite. I'm talking about picture C. Figure 7C, it's common. Another diversion is basically what you see in D. You turn towards it, and then basically you don't go further, you stop there. Then you have crossing, it's like crossing them as if they are not there. The crossing is what people believed was the case all the time back in the day. And you have a step over. You create this continuity, you cross it, but it changes your direction. And he managed to predict this behavior, considering the energy released. He made some nice plots with energy released. How does it help you understand, predict the behavior of the hydraulic fracture when it encounters the natural fracture? And also the angle at which it encounters it is very important. So yeah, if you go to the American Rock Mechanics Association Symposium, you will probably see him. He's there every year. I see him every year. We were office mates. Yeah, with Hanju.
Yeah.
Yeah. He got his PhD, I think, in 2015.
Louisiana?
No, Texas. And I got my master's in 2016. So yeah, we know each
He
other
was a
very well.
student
No, also.
also.
Very good guy, very helpful. Anyway, so this is what we mean here that they do play a significant role in permeability when it comes to those formations and also the fracture growth through them. The thing is that the shale around those calcite intrusions has almost no permeability, and these calcite intrusions could have permeability. That's why people write those dual porosity, dual permeability models.
Permeability factors, yeah. Even in simulation and commercial softwares, they have this window, like dual porosity.
Yeah. Even though most of those are for hydraulic fractures and rock, but you can also have natural fractures.
People are investigating through simulations the interaction between material fracture and hydraulic fracture.
Oh, yeah.
Yeah.
A lot of people. He was doing simulations, the same guy was doing simulations on PFC, which is particle flow modeling, not like what we do with continuum. And I think he had to have the simulations run overnight because it was taking a long time for every
Yeah,
simulation.
because people all the time talk about the angles between hydraulic fracture and material fracture.
Yeah.
It's pretty common and famous. They all the time talk about that and how it affects and compare of the production, like how it affects with the production.
Yeah, the more parallel they are, sorry, perpendicular to each
Yeah,
the bigger the chance for crossing.
like
To cross, yeah. But he did a better job with energy, the energy released or something. And that was the big part of his PhD. He did the other stuff too. But yeah, he was spending a lot of time in the lab. And he was my TA in geomechanics too. One of the two TAs. The other one was Dr. Kan Wu, who's a professor in A&M now.
oh yeah.
Yeah. PEFs can reactivate during hydraulic fracturing. That's what we saw. Such occurrences, micro to nano earthquake hypocenters, cause nano micro earthquake hypocenters, and are triggered by rock failure during hydraulic fracturing. Now it causes shaking, but it's not shaking that you can feel.
We call them an F or PEF.
Or PEF. MF is natural fracture.
And PEF,
Pre-existing fracture.
Same.
Generally speaking, pre-existing fracture has something inside it. Something else.
Field fracture.
Yeah. It's
Natural fracture is everything. Like.
Yeah. And they call it PEF. Yeah, something like that. Or beef, something. It's not pronounced as it looks for some reason. It's something different. It has something external, basically. It's not empty. Hydraulic fracturing triggers stress alterations that can reactivate some critically oriented PEFs in tight fracture reservoirs. This is different than what we do in the homework, which is we are injecting something to increase the pore pressure. Here, just hydraulic fracturing can reactivate some critically oriented PEFs in tight fracture reservoirs. These reactivated PEFs are useful to contribute in increasing the K of tight reservoirs at large scale, known as the stimulated reservoir volume. This is in shale. I'm doing hydraulic fracturing, and because of that, I get something like Hanju saw when he was basically splitting the calcite intrusion. I'm creating more and more, I'm creating a fracture network. So the fracture is not just, the flow doesn't come to the well through the fractures that I create. It comes through the well from also fractures that the fracture that I create. like natural fractures that are made to slip, etc., etc. Some of these reactivated PEFs may close and seal off fairly quickly upon reservoir depletion when the pore pressure goes down. Because remember, propan won't go into these fractures, right? So you will have to keep them open, but once you remove pore pressure, yeah, it's very easy to close down. You don't have anything preventing it from closing down. Now, what about an isotropy? Bedding plane orientation. This is something that is important, and we don't really talk about it. Most rocks have anisotropic stress properties. Therefore, UCS is a function of, i.e., depends on the loading direction. Okay, think about this. Okay, I have a test like this. Okay, I have a sample, and I'm gonna try to break it. Okay, what do you think will give me the lowest? What do you think will break at the lowest sigma 1, assuming sigma 3 is constant? What will require, which of the three samples will require less sigma 1 to break? Something that is layered like this, something that is layered like this, or something that is layered vertically like this. A, B, C. Which one do you think is gonna be easier to crack? Or it will crack at the lowest sigma 1?
Sigma 1 is vertical?
Yeah.
B.
Yeah. Why?
The friction angle.
You have layers in the direction of the.
I mean, like you will have like easy to reactivate the fault because you will have an angle of 45 degrees between the or 30 degrees between the horizontal. It's easy to reactivate.
60 degrees.
60 degrees, 45.
So I have layers in the direction that I'm trying to get to fail. So I'm helping it fail in that way. Okay, sometimes I may code, we used to do that in the lab for geomechanics when I was teaching, because after I took geomechanics the next semester I was teaching. We used to cut samples like this, cut samples like this, and cut samples like this. And the students had to run it and they were finding easier to break B than A or C.
Yeah.
And now what if B was like this? What is better easier to break right now? Same. Because it can break the other way as well. What will determine if it's gonna break like this versus like this? It's heterogeneities.
And sometimes it all the time breaks like that with conjugate
Yeah, you
shear.
can see it. Yeah, Espinosa used to take the sample after it broke, and he was taking it to the students to see that there was a
Conjugate
plane
shear.
of failure the other way as well.
The angle between them is 50 degrees.
Yeah. No, the angle of each of them is 60 degrees.
Between them, like this, and when you put sigma inside, you
Oh, yeah, it would be
it will
perfect
be
triangle.
30, 30.
Yeah. So yeah, I mean, yeah.
And it's very, it's one of the characteristics that you identify a tectonic zone that is divergence. You have divergence.
Yeah.
When you have divergence, you have Horst and Graben, right?
Yeah.
But default, they are like this. But when you go inside, you feel them like crossing like this.
Oh.
See, that's
Yeah.
sigma 1 you have like that.
Yeah, Horst and Graben, yeah. Normal faulting and reverse faulting.
Yeah.
These planes of weakness these are the layers, may be constituted by PEFs, weakly bonded layers, or weak rock layers. For example, there are some rocks with mica foliation, those are thin sheet layer mica, that exhibit almost no UCS whatsoever along the foliation plates. Like, it's very easy to move them across those mica foliation layers. Very, very easy to make them fail, almost like it requires no sigma 1. The rock is the weakest when the orientation of weak planes coincides with the plane of weakness. That's what Malek said with B, the B option. With the plane that meets the shear failure line, that is C equals pi over 4. Pi over 4 is like 45 degrees, plus phi over 2. So 45 plus phi over 2. What is phi? Phi is arctan, phi is psi. Sorry, no. Phi is arctan of 0.6, which is, hey Siri, what is arctan of 0.6? Yeah. I want to give you the exact value. Arctan of 0.6 is half radians in degrees. Yeah, 31. Let's just say 30. Okay. If it's 30, it's pi over 4 is 45 plus 30 over 2, 15. 30, you have 45 plus 15, that's 60. So, okay, so I will finish it here. I will carry on next time. Your priority for this class now should be homework 3. Start early, don't delay it. It won't be easy at the very end. Because it's not hard work, but it's a lot of work, like a lot of small stuff to put the spreadsheet together or the codes if you want to use a coding language. So yeah, don't leave it until the last day, okay? Thank you very much. Have a nice rest of your day. I will see you on Friday.